class for last week, which I was sick and couldn't be here. So I really appreciate you being here today. I would like to finish what we were discussing about nucleosynthesis in the previous class, and then I would like to talk a little bit about effective nuclear charge. And if we have a little bit of time, I would like to start with acids and bases, chapter 4. So in previous class, we were talking about how elements became to be elements. So at the beginning, at the very beginning, 15 billion years ago, there was no matter, there was no space, and there was no time. And the Big Bang happened. And when the Big Bang happened, all this matter got released and just came into existence. Space happened, time started, so our cosmic clock started to run. And we are here now. So about 3 minutes after the Big Bang, about 98% of everything that existed was in the form of hydrogen and helium. After a few billion years, we have reached still 98% of everything that exists in the galaxy, in the universe, is hydrogen and helium. About 26% of that is helium, and the rest is 24% is hydrogen. So we still have plenty of hydrogen and helium to go around. So we are not going to run out of hydrogen anytime soon. But that kind of like contrasts a little bit with the amount of hydrogen that there's in Earth, for example. So in the whole universe, most of it is 98% is hydrogen and helium. In Earth, less than 1% is hydrogen and helium. So many other elements are present here now. And those elements were created somewhere. And the factory for elements is necessarily stars. Stars have been the big factory that have allowed all the elements that we have, that we know today, to come to existence. So we're talking about the main sequence stars. Those were the first stars that appeared after the Big Bang. Those appeared about 400,000 million years after the Big Bang. Those stars burned hydrogen and fused hydrogen into helium, and very big stars were able to fuse helium into heavier elements. Eventually, those stars will become so massive, so hot, so dense that they will explode, releasing all these elements into the space. Every single element that is present here in this room, every single carbon atom that is making up your body, every single iron atom that is making up your hemoglobin in your blood, and the oxygen that you're breathing, all of that was built up inside a star at some time, somewhere. Some star, maybe 100 and maybe 1,000 million years away from here. All those elements were created inside a star. So basically, you are children from stars. You were created also there. Your building blocks were from there. So the thing is the following, or it goes like this. After those main sequence stars, so after those first generation stars exploded, then gravity took effect again, and these big clouds of gases start to coalesce again. And actually, our sun is a second generation star. It came from the debris that other stars have released into space. And we know that because our star uses hydrogen, the fuel of our star is hydrogen to produce helium, but it doesn't do what main sequence stars do. It actually uses carbon as a catalyst to fuse hydrogen into helium. And this is what we call the CNO process. is what our sun is. And basically, our sun uses carbon-12 to produce nitrogen-13 plus the gamma ray. This nitrogen-13 decomposes into carbon-13, a beta particle, and a gamma ray. Do you remember what I told you about beta particles? What are they? They're the same as a positron, right? Then, of course, that carbon-13 can combine with hydrogen or protium to produce nitrogen-14 plus a gamma ray. That nitrogen-14 can combine with hydrogen to form oxygen-15 plus the gamma ray, and oxygen-15 can decompose into nitrogen-15 plus a beta particle plus a neutrino. Oh, I made a mistake. This is not a gamma ray. These are sorry. So finally, nitrogen-15 plus nitrogen-15 can fuse with hydrogen to produce carbon-12 plus helium-4. So, these are the processes that happen in our sun. If you sum up all these reactions, you will realize that carbon-12 cancelled with carbon-12, nitrogen-13 with nitrogen-13, carbon-13 cancelled out with carbon-13 here, nitrogen-14 with nitrogen-14, oxygen-15 with oxygen-15, nitrogen-15 with nitrogen-15, and you will see that the next reaction that occurs is that basically 4 hydrogen atoms or 4 protons fuse to form helium-4 plus 3 gamma rays plus 2 beta particles plus 2 neutrons. This occurs at about 25 billion. These are the main reactions that happen in our sun. They actually use carbon as a catalyst, but if you look carefully, carbon is regenerated at the end of the reaction. So carbon really, the net reaction doesn't produce carbon. It just fuses hydrogen. That is basically all that I want you to know about nucleosynthesis. These are the reactions that occur in our sun. Other stars that are bigger stars are capable of fusing and producing other elements. But in general, all the elements that you see, including the very heavy, like lead and gadolinium and all these, have been produced in stars. The only exception, and I don't know if I told you this in the previous class, is lithium, beryllium, and boron. Lithium, beryllium, and boron cannot be created in stars. They are too unstable at high temperatures. They just decompose. So the lithium, beryllium, and boron that is present right now and currently in our universe, it was created either in the Big Bang or is created by cosmic radiation hitting and splitting other bigger atoms into boron, lithium, and beryllium. But those are the only 3 elements that are actually not produced in stars. Do you have any questions about nucleosynthesis? Well, if not, let's talk a little bit about the effective nuclear charge. Before talking about effective nuclear charge, can you tell me what is nuclear charge? Anybody? Do you know what a nucleus is? What it is? No, but a nucleus in general. It's a combination of what? Protons and neutrons, right? With the exception of protium, which only have protons, right? But it's a combination of protons and neutrons. So the nuclear charge is what? The positive charge that the nucleus has, and it's basically a number of protons that the nucleus has. So basically, that also defines the element. So the element is the element is defined by the number of protons that are inside the nucleus. Oh, okay. So the thing is this: have you ever been to a concert? Yeah. Well, concerts are generally very well staged because, for example, I'm standing right here. Imagine I am a rock star, which should not be that far away. And if I'm here singing, then you will be able to see me fine because your rows are kind of like in a stair-like fashion, so you can see. But imagine that it will not be like that. And I remember that when I was in New York, there were some concert halls that the stage was basically on the ground, and you would stand on the floor, and if you were in the first row, you would see very well. But then if you were in the second row, you would see so-so because there were people in front of you. If you were in the fifth row, then you will have to start try to move, try to see in between people to being able to see the stage. Well, what happens is that with atoms, it's basically the same thing. The ones that can see the stage, the electrons that can see the stage or that can see the nucleus, are the ones that are close by. So in a very simple atom, so let's say that a helium atom that has 2 protons in the nucleus, these 2 electrons and electrons that are in the first shell can see the nucleus very well. Those have no problem. The problem is when you start kind of like working with other elements. For example, lithium. So lithium will have 3 protons. But the 1s orbital can only be occupied by 2 electrons, right? So where the 3rd electron is going to be? In the 2s orbital, right? So now, the shell of the 2s orbital is a little bit larger, and the probability of finding that electron is a little bit farther away from the nucleus. So now, that 3rd electron, it can see the nucleus, but now it has 2 electrons that is blocking its frame of sight. So those 2 electrons that are here block this electron. So this electron cannot see well 3 protons. It sees something less because these 2 electrons now are blocking its sight. And that is kind of like the difference between nuclear charge and effective nuclear charge. The effective nuclear charge is the actual charge that the electron that is in an outer shell is capable of feeling. And it is defined or it depends of how far that electron is and how many electrons are between the nucleus and that electron. There are a few ways of estimating the effective nuclear charge. I'm just gonna talk a little bit about what we call the Slater rules. I'm not gonna go too deep into it because I'm pretty sure that you have already gone through it with Amir, but I just want to make sure that you understand this. We're going to call that. And the calculation of the effective nuclear charge is done by following the Slater rule. And there are, I think that there are 6 rules that you need to follow. The first one is that you need to write the electron configuration of your element, and then you have to group that electron configuration by codes. What I mean with that is this. Let me write this down so you can write it too. So basically you're going to write it in this way. I know that the way that you write the most stable electronic configuration might not be exactly this. But for the calculation of the Slater rules, you're going to just follow it like this. So you're going to put the 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f. Just in the way that I'm showing you. But you're going to fill it. You're going to fill the electrons in those orbitals in the same way following the AFCO rules that you know in the standard rule. Okay? So basically, once you write your electronic configuration in this way, what you're going to do is that you're going to group the 1s is its own group, well, the 2s and the 2p are in one group, the 3s and the 3p are in a different group. The D's and the F are in a specific group, so the 3D is a single group, the 4S and P's are together, B's are by themselves, and F are by themselves. So basically the only thing that you have to remember is that the 1S is in its own group, and the S and P's are always together. D's and F have their own group. So if you memorize that, you should be okay. And then, that is the first rule. The second rule is the following. Any electron in a group to the right contributes to no change. What I mean with that is, I erased it. So let's go back to it. It has 3 properties. So this electron is shielded by these 2 electrons that are in an inner sphere. But these 2 electrons are not shielded at all by this electron, which is out there. In the same way that if you are in a concert hall, you are not shielded from your side from people that are behind you. You're only being shielded by people that are in front. All right? 3. Electrons in the same group count 0.35 nuclear charge. So if you're in the same group, you shield not much, just a little bit, just by 0.35. 4. And I'm gonna yes.
The same group, do you mean the ones in
the ones that are in parentheses, right? And don't worry too much. We're gonna make a few exercises so you get a grasp of it, and it will become clearer. If the electron of interest is either S or P, let's put here S or P electrons. All electrons, maybe I should write this here. Number 4. S or P electrons. So the N value, as you know, is either here is 1, in the second shell is 2, in the third shell is 3, in the fourth shell is 4. So basically what it's saying is if you're here, value of N less than 1 will be here, and a value of N 2 or more will be here. Again, I know it might be, when you see the rules for the first time, it might be confusing, but you will get it once we do an exercise. The 5th, if the electron of interest is in an F or a D orbital, all electrons in groups to the left. Shielded by 1. So electrons in D and F orbitals are shielded more strongly. So everything, if you're sitting here, every single electron in other groups to the left shielded by 1. Actually, those are the easiest ones because we don't have to consider anything else. And finally, number 6, the sum of the amounts from step 2 to 5. Must be subtracted. From it. So that's it. Those are the slide rules. And with those 6 rules, you should be able to estimate the effective nuclear charge of basically any electron, or the effective nuclear charge that any electron feel if I tell you what electron. So let's do an example. Let's take a simple atom, like for example fluorine. Fluorine. If I tell you calculate the effective nuclear charge of an electron in the valence shell of fluorine. Well, the very first step is that you need to write the electronic configuration of fluorine using this, right? So how many electrons fluorine has? Yeah, you can cheat. You can look at the periodic table. 9 electrons, right? Out, neutral fluorine out. So that means that the electronic configuration will be 1s2, 2p2, 2s2, 2p5, right? So once I have it there, then what do I need to do? The parentheses, right? So where do I put the parentheses? Always one here, and then the other here. So I'm asking you to calculate the effective nuclear charge of an electron in the valence shell of fluorine. So then, how many electrons there are in the valence shell of fluorine? 7, right? Because you're going to use that whole group like as the valence shell and equals to 2, right? Okay, but you have to choose one of those electrons. So you choose one. That electron doesn't shield itself because you don't block yourself. So how many electrons are shielding one electron in the valence shell? 6, right? So 6 electrons times the shielding parameter that in the same group would be how much?
0.35.
0.35. Very good. So, of course, the electron that we are analyzing is in an S or P orbital. So what did we say about electrons in an S or P orbital? Value of n will shield by 0.85 and with 2 or more by 1. Okay, so I already took care of electrons here. Now I'm going to take care of these 2 electrons. So that those 2 electrons are what? It will be 1 or 2 or more.
1.
Right? N will be 1. So by how much those 2 electrons will shield? 0.85. Right? So if you do the calculation, which I have already done, then that will be 3.8. So that's it? What is missing?
You subtract the 9.
Now you have to subtract that 3.8 from what?
9.
This is what we call the shielding parameter. That 3.8 is the shielding parameter. So now you're going to subtract that 3.8 from the total charge of the nucleus, which will be what? 9. So the effective nuclear charge will be 9 minus 3.8, which will be what? 5.2. Right? Questions? You already covered this, right? So it should be pretty much clear.
Yes.
Did you do it with fluorine or with other atoms?
We did iron and zinc, I guess.
Okay, so let's do platinum, just to make sure that you understand. What about if I tell you to calculate the effective nuclear charge of an electron in the 6s orbit? The effective nuclear charge of an electron in the 2s orbit. Go ahead. I'm going to give you, I don't know, 1 minute. The 6s. Although I can ask you to do it in the 5s or the 4s, but 6s sounds good. Did you do, Amir, electrons in D and F orbitals?
Yes, yes. And we also did the cation. So we did, yeah, neutral and,
So I'm not going to cover any of that. You already done that. So.
yeah.
Are we done? just to finish this. So remember that you're gonna write the electron configuration, but you're gonna fill it up as you actually as you do with the APO principle, right? So basically, there's no problem with these. They're completely filled up to 4F14. Here is fine. Here you have to have the 5D8 because the 2S are more stable, right? So, and the 5X doesn't get filled yet. They're there, and you have to leave it there, but they don't get filled. So that is important here. And of course, the T are not filled, so they're 0. So if you do that correctly, then the rest is just counting electrons, right? If you're in the 6S, then how many electrons are chilling you in the same group? Just one, right? So then just write 1 times 2035 plus how many electrons are in an n-1 group? Well, an n-1 group is basically all these. Right? So how many electrons are there? 16. So 16 times what? 0.85. Plus, how many electrons are in n-2 or more? Sorry? 60 electrons. So 60 times 1. And if you do that calculation, that must be 73.95. And of course, that is not the effective nuclear charge, that's just the shielding parameters. So then you subtract the effective nuclear charge, which is 78 minus 73.95. And that gives you what? 4.05. So if you got that, then you're right. Any questions? If you have any questions at all, you can ask me. You can ask me, or you can ask Amir, and you will be fine. So if you don't have any further questions, then I would like to start talking a little bit about acids and bases. So acids and bases. This is not the chapter. So acids and bases are basically one of the things that you learn very well during general chemistry. Here we're gonna try to go a little bit deeper in what acids and bases are and why they are important. Many of the reactions that we actually study in inorganic chemistry are acid and base reactions. And there are very simple definitions for acid and bases, and there are very complex definitions for acid and bases. So the most simple, or the simplest definition for an acid and a base was given by Arrhenius. And do you know the Arrhenius definition for an acid and base? What do you think is an acid? It's a proton donor. What else? Proton donor, Bronsted definition of acid and bases. Electron pair acceptor, Lewis definition of acid and bases. Arrhenius definition is basically based on the Bronsted definition of acid and bases. But Arrhenius says that an acid is a substance that will donate electrons when placed in water. So notice that the Arrhenius definition defines the solvent. Defines the solvent as water. A base is basically the opposite. An Arrhenius base is a substance that subtract or react with protons when added to water. The definition of Bronsted doesn't include solvent. So an acid is a substance that donates protons regardless of the solvent in which it is placed. And a base is a substance that reacts with those protons or that get protons when placed in any solvent, in whatever solvent you define. The Lewis definition of acids and bases, we will discuss it later because it's related to complex formation. And those are important concepts in the formation of bonds in molecules. But we can use the opportunity to actually study some of these concepts. So, one of the most interesting observations about acidity in water and something that we call autoprotolysis of water is that protons in water move extraordinarily fast. Protons in water move faster than in most solvents. The rate of transport of protons in water is about 3 times faster than in other solvents. And that is a little bit odd, but actually when you kind of like think about it, it makes sense. Protons in water are transported in something that is called the Grotthuss mechanism. In water, an H3O molecule will basically donate protons to a water molecule in a very fast way. So the proton, instead of proton moving from here to here to here, now this proton can be transferred to another molecule. Instead of the proton being moving, the proton hop from one water molecule to another, and then it's not the same proton, the one that hops to the other molecule. So basically the speed of that transfer is very fast, and the movement of protons is fast as well. Because it doesn't require the protons to actually move. They can just couple to a water molecule and a different proton can jump to another water molecule. So this process is very fast. It's about 1 to 4 picoseconds. So that makes the proton transporting water relatively fast process. And this is related to the ability of water to behave as an acid and as a base. Just to review some of these concepts, for example, give me a base. What base do you know? The most famous, one of the most famous bases is sodium hydroxide, right? So you put sodium hydroxide water, what happens?
Hydrogen transfers.
Well, you basically, okay. completely dissociate, right? So you have hydronium atoms all the time. Sodium hydroxide is not a bad example because basically what's going to happen is it's going to stay dissociated. So you're going to have sodium hydroxide all the time. Let's use a base that doesn't have OH. Give me a base that doesn't contain OH. Ammonia, NH3. So what happens if you put NH3 in water?
It gains a proton.
What do you produce? NH4. Liquid ammonia can be mobile as a gas. NH4 plus what? Plus what? OH minus. Do you remember what is the acid there?
Ammonia.
Water. What is the base? Ammonia. What is the conjugate acid?
Ammonia.
NH4 plus. And what is the conjugate base? Sodium hydroxide, right? I mean, not sodium hydroxide, hydroxide, OH. Right? Those are concepts that you remember from general chemistry. Very good. So, all right. So, if all of these will be in solution, so if ammonia is already aqueous ammonia, and this is in water, then I can calculate the equilibrium constant for this process, right? How do you call the equilibrium constant for basic equilibrium? Like the Kb, right? So what would be the Kb for this? Well, we can do it for a general Hb plus H2O producing B plus OH minus. So the Kb will be the concentration times divided by what? If we go there, it will be just the concentration of OH times the concentration of NH4 divided by the concentration of NH3. Water is a solvent, it's in excess. The concentration of water basically doesn't change, so it's basically not included. So you probably remember all this. We can express this as a base, the Kb, the basic equilibrium, or we can calculate the acidic equilibrium as well if we have an acid. So if we will have an acid, I mean, in this case, I'm sorry, I actually made the Ka. This is the acid equilibrium. The basic equilibrium should start, sorry?
It should be H2O plus instead of OH minus.
Yeah, I'm sorry. This is the this is the this is the basic equilibrium. Yeah, I messed up the two together. Sorry for that. So that is the basic equilibrium. The acid equilibrium will be the formation of H2O plus, and the Ka will be and let me see here, and here will be of course, by looking at these equilibrium constants, immediately you can get some sense about what is a strong acid and what is a strong base. In the sense of Ka, a strong acid will be anything that will have Ka larger than 1. And a very strong acid will be something that have a Ka way larger than 1. So I don't have my slides here today, unfortunately, but that is basically the main Kb. The same is for base. A very strong base will have a Kb that is larger than 1. And a very strong base, like sodium hydroxide, will have a Kb that is way larger than 1. There's another concept that you probably know already that is called, and we were talking about it when we were talking about the Grotus mechanism, that is what we call the autoprotolysis. So the autoprotolysis is basically related to the ability of a solvent to protonate itself or to act as an acid and a base. And in the perfect example is the water molecule. So for example, two water molecules, one water molecule can act as an acid, the other water molecule can act as a base. So two water molecules can actually form H3O, H plus hydroxide. And of course, this is another equilibrium constant that you know very well. This is called the K. And for water, the Kw has a fixed value, which is what? 10 to the negative 14, right? Very good. So, there is another thing that we like to call the pKa, no, the pKw, sorry, which will be what? 14. And how do you define pKw? It's the negative logarithm of Kw, right? Or the negative W of any constant. For example, pH will be what? Negative log of the concentration of H3O, right? So, a strong acid will completely dissociate in water. So if a strong acid is something that has a Ka larger, if a strong acid is something that has a Ka larger than 1, then the pKa of a strong acid will be what? Less than what? 0. So a strong acid will be something that has a pKa smaller than 0, right? The same with a strong base. A strong base will be something that will have a pKa smaller than, a pKb smaller than 0. All right. So there are, let me see, there are three different kinds of acids that I would like to discuss, and I will probably finish with that today. Three different kinds of acids. So the first kind of acid is what we call the aqua acids. So the aqua acids are acids in which the acidic proton resides in a water molecule. Let me write that down. There are many examples, but basically any metal ion or any metal cation that you can think of can act as an aqua acid if it is dissolved in water. For example, lithium, sodium, aluminum, iron, titanium. They can all act as an aqua, as aquas. And basically, the reason for that, let's take any of these, iron 3. When you dissolve the iron 3 cation in water, basically it is not just like that there. Basically, water molecules point their non-bonding electrons toward hydrogen, toward iron, and will coordinate iron octahedrally. Of course, iron is a highly charged metal cation, so it has a +3 charge. So, what do you think is going to happen when this positive charge interact with the negative charge of these electrons here? What do you think that? What happens with positive and negative charges? They do what? They attract each other, right? So the strong positive charge of iron actually pull some of the electron density from the oxygen atom. And when it does that, the bond between the oxygen and the hydrogen weakens. That bond becomes weaker. And what that will produce is that one of these hydrogens will be lost. So it will transfer the hydrogen to the solvent. And that is what all these metal cations are good aqua acids. They will transfer electrons, they will transfer protons from the water that are coordinated to them to the solvent. The higher the charge of the metal, the stronger will be the aqua acid. We will discuss that a little bit in next class, but we talk a little bit about the electrostatic parameter. But for now, you just have to know that metal cations tends to be very good aqua acids. The second kind of acid is what we call hydroxo acid. So hydroxyl acids are interesting, and they're based on aqua acids, but in this case, the proton is transferred not from a water molecule, but from an hydroxyl one, or from a hydroxyl one. Proton transfer from a hydroxyl. And examples of this are, for example, silicon hydroxide, or tellurium hydroxide. In these cases, the proton is transferred to the solvent from a hydroxide. And finally, let me write this a little bit higher. Finally, the third kind of acid is what we call the oxoacid. And the oxoacid is defined as an acid in which the proton is on a hydroxyl group. With an oxo group. At the same time. And of course, this is the kind of acid that you know very well. For example, sulfuric acid is one example. H2SO4. Phosphoric acid is another example. H2PO4. Phosphoric acid. H2PO3. When you have oxo groups that don't contain any protons. And actually we will discuss in the next class why these oxo groups and how the amount of oxo groups in this central atom actually affect the acidity of that proton that is in the hydroxyl group. We will discuss how the size and the charge in aqua acids basically affect the strength of these acids. And we also will discuss how different oxides in different groups in the periodic table are either basic, acidic, or amphoteric, depending on where they are and how they position in the periodic table. So for now, I think that I can let you go with that. Since we have class tomorrow, I think we'll be fine. So, do you have any questions? So if not, I'll see you tomorrow.